Hello, this is Lab 2, Motion of Falling Objects. In this lab, we're going to examine Newton's second law by analyzing the motion of a falling object and compare it to modeled simulations based on Newton's second law. Newton's second law states that the acceleration of an object is directly proportional to the force and inversely proportional to its mass. And by the end of this lab, we want to know if Newton's second law is good or not at predicting the motion of a falling object. With the observation, a falling object was recorded using a phone camera and uploaded to Tracker to be analyzed. On the bottom right, you can see the table with all of the data points, and on top of it, you can see the graph. The calibration stick was used to set the height of the object, and the X and Y axes were positioned at the top tip of the object. Now let's look at the data collection in action. This is a graph for the observational data. So this is the code for the first model. As you can see, the time was taken from the last observed data point. We use the velocity update formula with the acceleration due to gravity, and we use this formula for the average velocity since the force is constant, and then we use that in our position update formula. We use this model because we want to know if the gravitational force is the only force acting on a falling object or not. This is the graph of the model. This is the animation. This is the code for the second model where we consider the drag force as well. So in this model, we assume the coefficient to be given such that the acceleration due to the drag force is equal to the velocity squared. And then we add that acceleration to the acceleration due to gravity to obtain the acceleration that we used in the velocity update formula. And then since the force is now constant, we approximate the average velocity to be equal to the final velocity. And then we use that in the position update formula. This is the graph for the model. And this is the animation. This picture illustrates the progression of the drag force. Since the drag force is proportional to the velocity squared, it increases as the object speeds up, meaning that the downward net force decreases as the object speeds up. The drag force keeps increasing until it's equal to the gravitational force, resulting in a net force of 0. When the net force is 0, the object's velocity no longer changes. This means that the drag force stops increasing. At that moment, the falling object reaches a constant velocity known as the terminal velocity. Now let's compare the velocity graphs of the two models. The constant change of velocity of the blue curve reflects the constant force of gravity. On the other hand, the red curve shows the effect of the drag force. As the object's velocity increases, the drag force increases and the net force decreases. The decrease in the net force is demonstrated by the decrease in the steepness of the curve. The net force decreases until it reaches 0, where the slope of the curve is 0 and the object reaches its terminal velocity. This is what the graphs look like in comparison to one another. At the beginning, they move together, meaning that the predictions are accurate. But after a very short period of time, the blue curve starts moving away from the other two curves. And since the first model doesn't predict the motion of the curve of the object very well, this proves that the gravitational force is not the only force acting on the falling object. However, the other model keeps predicting the motion accurately until it reaches a point where the two curves are separated. This separation is caused by a poor approximation of the drag coefficients, which led the model to reach the terminal velocity too early, while the observed object is still accelerating. Possible sources of error include blurriness of some frames of the video and an unstable camera, which lead to inaccurate collection of data, and also rotation and slight movement along the X or Z directions. How to improve them? Well, we can record the motion with a more stable camera and use a better camera that captures individual frames of video with a higher quality, which leads to more accurate collection of data. We can also approximate the drag coefficient instead of assuming it to have a certain value. That way we can have a better prediction. Let's imagine throwing the object downward instead of dropping it from rest. What would that change in terms of physics principles? Dropping an object from rest means that the object has 0 velocity when it's released. On the other hand, throwing an object downward means that it has a non-zero velocity when released. Using the second model, different initial velocities were tested and graphed. As you can see here, no matter what the initial velocity is, the object eventually reaches its terminal velocity. If you consider the situation where the initial velocity is less than the terminal velocity, a downward net force would cause the object to accelerate. As a result, the drag force would increase until the net force is equal to 0 and the object reaches its terminal velocity. If we consider the case where the initial velocity is greater than the terminal velocity, the drag force would be greater than the gravitational force, resulting in an upward net force. Applying an upward net force to an object moving downwards decelerates the object and slows it down. As the object slows down, the drag force decreases until it's equal to the gravitational force, resulting in a net force of zero. That's when the object reaches its terminal velocity. In conclusion, Newton's second law is good at predicting the motion of a falling object only if you consider all the forces on the object, which in this case include gravitational force and drag force. This is the end of the presentation. Thanks for listening. Have a great day.